Hello everyone, this is Mr. Slamka, and I wanted to talk to you guys about section 7.3, which is proving that a quadrilateral is a parallelogram today. Right off the bat to begin with, I know it says that we're going to be doing some proving today, and we're going to be talking about a couple of different theorems or converses today, but I don't want to write a full-out proof, so if that word right there stresses you out, hopefully we can reach a bit of a compromise where something is has a lot of information in it, but isn't necessarily a full-blown proof. So let's just focus on our theorems right now and see if we can get used to that, and then we'll get to that whole proving, not proving thing in a little tiny bit. Okay, so to begin with, at the top of the page right here, what I have is I have 4 theorems. They're very similar to the ones that you learned about with Mr. Merlot in the last video. Mine are the converses, which means that they are backwards. So what we're going to do is we're going to start off with some very clear information, and then we're going to end with the fact that these guys are parallelograms. So let's go through them. So to begin with, we have parallelograms, opposite sides, converse. So now the opposite sides converse states that opposite sides are congruent, and if that is true, then what the shape that you're looking at is in fact a parallelogram. So that's a really, really great one. Not a surprising one. Second one, opposite angles converse. And once again, if you start off with the angles that are opposite and congruent, that means that the shape that you're looking at is in fact a parallelogram. So Mr. Merlot had talked to you about parallelograms having opposite angles being congruent. Mine is backwards. I start with the angles, and I get to tell you that it is now a parallelogram. Third one right here, parallelogram, diagonals, theorem, converse. This one starts off with both diagonals going to bisect each other. So this point M right here is called M because it is a midpoint. And you have 2 sets of congruency on either side of the diagonal midpoint. And then the last one. This one's a really, really great one. This one's called the opposite sides parallel and congruent theorem. And this is going to be one that is not a converse. This is not one that Mr. Merlot talked to you about yesterday. This is just going to be a bit of a new one. This one states that if you have one set of sides, just one, not 2, but 1, and the set of sides is both parallel and congruent, that means that you have a parallelogram as well. So now that one right there is a little bit different because you're talking about 2 different kinds of pieces of information, parallel and congruent, and you're only talking about one set of sides. So that one's a special one. So what we're going to do today, the goal for today, is to get ourselves as comfortable as we can with these 4 theorems and so that you can use them and reference them as often as possible and know when something is a parallelogram. Let's take a look at a couple of examples. So down here at the bottom of the page, we've got a couple of examples that I'd like to go over with you right now. It says we have quadrilateral ABCD, and we've got a couple of side lengths that are going to be equivalent to each other. Notice that there's no lines over top of any of these letter combinations because we're just talking about the distances. The question is ABCD a parallelogram? And you need to explain your reasoning. So what I've done right here is I've drawn you a small little quadrilateral. Yes, it looks a little bit like a parallelogram, but we're going to have to decide if it is actually going to be a parallelogram. First thing I've done here is I've labeled the corners. Now I've labeled them in the exact same order that you see in the write-up. So it's going to go A to B to C to D. I chose to go clockwise. You could go counterclockwise. I chose to start in the upper left-hand corner. You can start in any corner you want. Okay, so now let's do some labeling. In my labeling right here, it says that AB is going to have the same length as BC. And it says that CD is going to have the same length as AD. Now right off the bat, the first thing that I'm thinking about is the parallelogram opposites converse, which states that if you have 2 sets of congruent sides that are opposite, you have a parallelogram. So if you are just moving fast, you might think, yes, this shape that I have drawn looks like it's going to be a parallelogram. But let's mark them. So now AB is the first one I want to mark. I'm going to mark it with a single tick mark. And then BC is the other one that is going to have the equivalent length, and that one also gets a single tick mark. CD is going to be another set. It gets the double. And then AD gets the double as well. Now I want you to notice that there are 2 sets of congruent sides, but what I'm really looking at is 2 sets of congruent sides that are not opposite. These 2 sides are adjacent, and these 2 sides are adjacent. To be fair, this drawing is a little bit of a throw-off because what should really happen is that the shape should look like this, where you have 2 short sides right next to each other, and then another 2 sets of sides that are going to have the same length. So this guy is not a parallelogram, and that guy is also not a parallelogram. So what I was thinking was it was going to be parallelogram opposite sides converse, but it turns out that that is definitely not the case. So this guy right here is not a parallelogram. Is ABCD a parallelogram? The answer to that question is no. And explain your reasoning. And whatever they mention, explain your reasoning in a geometry class, what they really mean is give me a good theorem. And the theorem that we're going to talk about is the parallelogram opposite sides converse. If you've had Mr. Slomka before, you know I love to simplify or abbreviate these theorem names, and so I've done that right here. Parallelogram opposite sides converse is going to tell us that no, this is not going to be a parallelogram. All right, let's do another one. So our next one right here is an example that is always nice to do. If you take a look at the picture, you can already start to see a couple of their algebra expressions popping up here, so these ones are always great. So this one says, for what value of x and y is the quadrilateral STUV a parallelogram? So STUV is already labeled for us, which is great, and it certainly looks like a parallelogram, but we need to see if we can set some values for x and y that will make sure that is true. Once again, the theorem that I'm interested in is a theorem that is going to be about side lengths. So the best one for side lengths is the one that says side in the name, which is going to be our parallelogram opposite sides converse. So this one once again states that opposite sides, like the left and the right, or the top and the bottom, have got to be congruent to each other. So let's use that to our advantage this time. Let's make them congruent, as opposed to last time where they were not congruent. So what I'm going to do is I'm going to use the left side and the right side, and I want these two pieces to have the exact same length. So I'm going to set them equal to each other. And when I do that, now what I have is an equation that I can solve very quickly and easily. I'm going to solve it by moving my x terms together. I know a lot of times people want to move their numbers together first, but I am a big fan of moving my variables together to begin with. So I'm going to do that. That's going to give me 24 is equal to 2x plus 6. Then I'm going to move my numbers, my 24 and my 6, a little closer together by subtracting 6. And that is going to give me 18 is equal to 2x. And then lastly, I'm going to divide by 2. And I'm going to get 9 is equal to x. So if you use a value of 9 for x, then the left side and the right side will have the same length. And that is easy to spot. If we look over here on the right side, 9 plus 6 would give you 15. And over here on the left, if we do 24 minus 9, that will also give you 15. So it's worked. It has made the two side lengths the exact same. Now we need to do the same kind of thing for our y variable as well. So let's work on that one. So now the y is a bottom edge, and so that means its opposite, which is the top, needs to be equivalent. So I'm going to take my y and I'm going to set it equivalent to the top, 2x plus 3. Now, I'm not a huge fan of this equation right here because it has a mix of two different variables in it, and so I would like to see if I can change that. And the way that I'm going to do that is by using my last answer. I know that my x value is actually equal to 9, so I'm going to be able to replace this x variable right here with a 9. There you go. And now what I can do is I can simply simplify what's going on over here on my right side, and my y variable will come up with a good answer. So 2 times 9 is going to be 18. And then 18 plus 3 is going to be 21. So if you have a y value of 21, that will also make it so the top and the bottom match the same way that the x's matched earlier. All right, down here at the very bottom of the page, I have a you try it problem. And what I'd like you to do is I'd like you to pause the video and try that you try it problem now, and then I'll give you the answer in a couple of minutes. Here's the answer for your you try it problem. This question is about diagonals, and so you're going to want to pick the parallelogram diagonals theorem converse to kind of set yourself off. The diagonals should be congruent just like the side lengths. And so I'm going to set my two diagonals congruent to each other and solve for x. And when you do that, over here, once again, 5 times 3 is going to be 15. And over here on the right side, 2 times 3 is 6, and 6 plus 9 is also 15. So it will work, and both of the diagonals will be bisected, so that works out great. One of the things that I really like about this lesson that hopefully you're starting to see is that if it looks like it's true, it probably is. So like for a parallelogram, at the top and bottom look like they're the same length, and that's because they are. And in a parallelogram, opposite angles look like they're the same size because they are. And in a parallelogram, diagonals look like they've been cut in half because they are. And so as long as you're following your gut, you should be pretty safe. Just watch out for some of those tricky cases like this one right here. All right, let's move on to the back side. On the back side, okay, on the back side, what we have right here is we are going to start on those proof, not a proof things that I was talking to you about that we were going to try to reach a compromise on. So what I have for you right down here is I've got a couple of problems, and the problems are going to state that they want you to prove that a quadrilateral is a parallelogram. And that is something that I'd kind of like to work towards, but if you look closely, also you'll notice there's no t-tables right here. We're not going to be filling in a t-chart with the actions and the purpose for your actions. We're going to try to do it a little bit more informally so it's not so hard on you, because I know that proofs can be no fun for some of you, and others of you really enjoy them, like me. And so what we're going to do right here is I want to talk to you about a couple strategies, and as usual, I want you to show some work, and as usual, just like on the front side, I maybe want you to state which theorem you were talking about when you were writing the stuff down. So here we go. Okay, so to begin with, what I have right here is I've got some strategies for you. So now these strategies are very, very nice and clearly laid out for you with some formulas so that you can work through them very quickly and easily and know exactly how to attack this whole proof situation. So let's talk about it. What we're trying to do, once again, is we're trying to prove that something is a parallelogram. So how do you do that exactly? Well, here's a couple of strategies. Strategy number one. What you can do is you can prove that your quadrilateral has two sets of parallel sides. And so that means you need to show that something is parallel. And the best way to do that is by using slope. Lines that have the same slope are always parallel. So I have your slope formula right here. If you start calculating slopes, it's going to help you decide that things are parallel. So it's a great way to go. All right, second one. Today we had talked about the parallel opposite sides converse, which means that if you know that the opposite sides have the same length, then they are going to be parallel. So I have the distance formula right here. You might need to calculate the distance formula 4 times. And then, if you find that you have two sets of matching sides, you're good to go. Third one. Opposite angles can be congruent as well. So now I don't have as many great angle formulas for you, but the one that I have that Ms. Turbrack taught you about in section 7.1 is this guy with the angle sum theorem. If you take all 4 of the angles from the quadrilateral and add them up, they should add up to 360, and then you can use that to determine if you have two sets of matching ones. Fourth one is the new one for today, the one that was not a converse. And this is going to state that you have one set of sides that is both congruent and parallel. So you'll notice I have two sets of marks on the top and the bottom right here. The first set of marks is about congruent, so you'll need the distance formula for that one. The second set of marks that look like the arrowheads is for parallel, and so you'll need slope again for that one. So this guy right here is a little bit of a mix of the top two, and it is going to be a mix of the top two, but only for one set of sides. Last one right here is the one about diagonals. And so now this one can be interesting because you can come at it from a couple of different perspectives. The main thing that you can do right here is you can look at the diagonals and you can match up the two sets on either side of each diagonal, and you can use the distance formula to show that they're congruent, or you could potentially use the midpoint formula right here to show that they are going to be intersected at the midpoint right here in the middle. All 5 of these strategies work really well. The main challenge for you is going to be to decide which set is going to be the one that you like the most. I know, in general, most of the time, kids like the top 2 the most, specifically the second one. It's very straightforward. It works well. They know how to use the distance formula. They're comfortable with it. It is a little long. The distance formula is not a short formula, but it does work well. So let's try it out. Okay, so now what I have for you right here is I've got 3 examples, and I'd like to get started. So now for our first example, this is also our most general. I want you to notice that this picture looks like a parallelogram, and it is laid out on an XY axis, which gives us a lot of freedom, because some things that you can do on this XY axis is you can do a lot of counting, and you can find a lot of different pieces of information. So let's talk about some info we could get. On our parallelogram, or on our quadrilateral right here, we could find slopes very quickly and very easily if we wanted to, and then you can compare slopes. Other things you can do, you can measure distances. You can find the length of each of these diagonals super quickly and super easily, and so we could do that as well. We can draw in our own diagonals, and then we can find the midpoint of those diagonals, and that would work super well. All of these options are available to you because it's all drawn on an XY axis. You just have to pick the one that you like the most. So, as I stated, most of the time people really enjoy option 2, which is going to be parallel sides or opposite sides converse. So I'm going to go with that one right there, but it might not be your favorite, but I think it's still going to be the one that appeals to the most people. If you're thinking, well, I wanted to do it a different way, then please do it a different way. Your way will probably be a little bit faster, and you'll like it more, which means it'll be a good, successful choice for you. Any of the geometry teachers would be happy to see any of the options that you have for them. Just try to be clear and try to show your work. So let's do it. So the first thing when you're working on one of these problems is you want to choose your method, which I've already chosen, and then you want to show some work to back it up. So because I'm choosing option number 2 right here, I'm going to use the distance formula a couple of times, specifically 4 times. And so that means that I am going to be calculating the distance of the 4 sides. When I calculate this distance, I'm going to try to be clear. So I'm going to start off with the top side, which is KL. And so I'm going to say I'm working on side KL, and then I'm going to set up my distance formula for it. So when I'm setting this up, I'm going to use my x values first and my y values second. So I have my x values and my y values all listed right here, so I don't have to do very much work for them. And it looks like this. Then I can perform my subtraction, and then I am going to get something that looks a little bit simpler, and I'm going to get it all the way down to this. And now this square root of 8 right here, if you type it into your calculator, you will get a decimal. And I don't really want that decimal. You could simplify this if you'd like, and that would be really, really nice. It simplifies down to 2 root 2, but that's also a little bit of extra work that we don't really need to do. So we're just going to leave it right here at square root of 8, and we're just going to see if we can get another square root of 8 from some of the other sides. So let's do that next. My gut tells me that if this top side right here looks pretty short, I should match it up with another short side. So I'm going to look at NM next. So NM right here is going to have these two sets of points, and I'm going to calculate the distance formula a second time. I'm going to start with my x values again, which is going to be 6 minus 4. And then I'm going to use my y values, which is going to be 0 minus a negative 2. Minus a negative is going to be plus, and so we are going to end up with 2 squared and another 2 squared. Right away, I can already tell that I'm getting something very similar to what I had before, which is good. It's what I expected. And as I was saying on the front side, what you think is true is probably true. And so we are going down a very similar path, and we're going to get a similar result. Great. Okay, now I'd love to call it quits right here. And if you picked some of the other options down here, you might be done by now. But because we chose opposite sides, what we're going to do now is we're going to have to do the same set of work again for a second set of sides. So let's see if we can find that as well. So my next set of sides are going to be a little bit longer. Let's look at Kn this time. So for Kn, what I want to do is I want to use my endpoints over here on the far left side. This is a much longer side, but the technique is still very much the same. So here is our x values right there. Let's do another round with our y values. This is interesting because we're going to have a 2 and we're going to have a negative 2. Oops. There we go. So I've got my 4, take away 2. I'm working from the bottom to the top. And I've also have my negative 2, take away 2 again. All right. So now my 4 take away 2 is going to give me another 2 squared. And my negative 2 and my negative 2 is going to give me a negative 4. Now 2 squared is still 4, and negative 4 squared is positive 16. So make sure you're careful there. Even though it is negative, when you square it, you do get a positive value right there. And then once again, we are going to add these two guys together, and we're going to get the square root of 20. Now, just like before, square root of 20 is not very nice. You could type it into your calculator and get a decimal, but I certainly don't want that. You could also simplify this, and you would get 2 root 5. But I'm not super interested in that. It's not going to make the biggest world of difference to me if you do that, so we can just leave it as the square root of 20. Let's do one more round of this, and we're going to look at our last long side, which is LM. And for LM, you're going to need to do the same set of work all over again. So our final distance formula. So now one of the reasons that I'm showing this is because I want you to see how long it is, and I want you to maybe think to yourself, maybe next time I'll use a different technique that it might be a little bit quicker because this one is a bit long. In my opinion, I think for this problem, my favorite technique is the diagonals one because I think it works pretty quickly, but I know that once again that might not be your favorite. So I always want to try to help you out and give you the one that makes you feel comfortable so that you can always reach for it and use it when you'd like. So this is our last round right here. We're going to end up with our 2 squared in front again and our 4 squared in the back. This time the 4 squared is positive though. That's fine because positive 4 squared and negative 4 squared give you the same answer, which is still 16. And we're going to end up with another root 20. Okay, so now let's do a little analysis. I've got a little bit of work right over here, and I want to fill that work in with a little tiny write-up. Not a ton, just a little bit. So here's a couple things I'd love for you to do. Yes, you've shown me all your work, but I want you to state it very clearly. And so some clear things that I would love you to say is I would love you to point out the fact that KL and NM were the ones that had the same length. So I'm going to state that on my page. KL is congruent to NM. We also did the same kind of thing over here with KN and LM, and so I'd love to state that those two are congruent as well. So make it clear exactly what you're trying to show. So we're trying to show that the side lengths are the same, and we've written that down right here. Now, the very last piece that I want you to do, this one is a very, very important step, and it must be completed very thoroughly. And then what we're going to do right here is we're going to name our quadrilateral, we're going to state that it's a parallelogram, and we're going to say why it's a parallelogram. So this is a 3-part process. First thing, let's name it. So I'm going to call it KLMN. I'm going to say it is a parallelogram. And I'm going to state that it is a parallelogram by, and I need to pick one of the theorems from the front side. So our options from the front side are, once again, these guys right here. The one that I was using was the top one about the side lengths, and it was the parallelogram opposite sides converse. So this is what it's going to be parallel by. It's going to be parallel by the parallelogram opposite sides converse. There you go. So you name it, you say that it's a parallelogram, and you tell me why it's a parallelogram. So there you go. You're going to show some work over here. You're going to write down a couple of clear facts, and then you're going to kind of conclude the whole situation right here. So this isn't a full proof, but it is going to help us understand whether something is a parallelogram or not. Okay, so now let's move on to our next 2 examples. Our next 2 examples are in the same section, so we do want to do the same thing, but we've been given some more clear information. Now, I liked this question because it was so general, and you could go in a lot of different ways, but the next couple I like as well because they're going to kind of force you to pick some of those more different ways that you might not like as much. So let's look at the one that's right below it. Right down here, what we have is we have a parallelogram that I've chosen to name ABCD just to help myself out. And I notice that it's got angle measures in there. There is no information about the side length, so you can't go back to the one that you might like the most, which is the parallelogram opposite sides converse. So I'm going to be forced to talk about angle measures. And so the one theorem that we have that is about angle measures is our opposite angles converse. So I'd like to see if we can create a couple of sets of opposite angles. So let's do it. So what I'm going to do right here is I'm going to notice that I already have one set of opposite angles here, and I want to have another set right here and here. The best way to determine what the measure of angle B is once again to use the angle sum theorem, which is going to state that all 4 of these angles need to add up to 360 degrees. So if I take 360 and I subtract from it a couple of 61s, whoops, and if I subtract from it a 119, I should end up with the measure of angle B. If you do all of the subtraction, not very surprising, you end up with 119 degrees. Wow. And so I'm going to put that on my drawing. And now I'm going to see if I can finish this proof off. See how much quicker this one is? This is really nice. This one is, once again, somebody's favorite, but it is also a pretty slow one. So what I'm going to do right now is I'm going to try to state a couple of clear facts. And the facts that I want to state is I want to state that angle A is congruent to angle C. They have the exact same measure. I also want to state that angle B is going to be congruent to angle D because they have the exact same measure. And now that I've done that, I should be able to once again name my shape, call it a parallelogram, and tell why it's a parallelogram. So I'm going to call this one ABCD. ABCD is parallelogram. And it is a parallelogram by, and the theorem that we're using this time is parallelogram opposite angles converse. There you go. Okay, so this is it. This is the only piece of work that we need to show, and then we need to make a couple statements, and we're good to go. Let's do another one, our final one. So our final one right here is going to be this guy right up here. And so for this guy, what I want you to notice is I've given you quite a bit of information, but it's only about the very top side and the very bottom side. So this is a bit interesting. There's no information on the left or on the right. There's no information inside the parallelogram. So this is going to once again kind of force us in a particular direction. Knowing about only two sets of sides is going to kind of force me to go down this road, the opposite sides parallel and congruent theorem. So this one is an interesting one because they need to have the same length and they need to be parallel. So we're going to see if we can state a couple of those things. The other interesting thing about this problem is you'll notice that there's no numbers at all, which is going to make it a little trickier. So you're going to have to make sure you can get all the information you need, and unfortunately we won't be able to use any theorems at all, or any formulas, I should say. So let's do it. So one of the things I want you to notice about these guys is that they're actually labeled with a length. So the length of WX across the top is a length of A, and the length of YZ across the bottom also has a length of A. So even though it's not a number, it does match, which means that what we can do is we can state that WX is congruent to YZ. Interesting. You'll also notice that they are both labeled with these arrows, and those arrows mean that WX is parallel to YZ. So this has far less work. There's very little to do right here except to state what is clearly labeled on the drawing. And then, because we have all of this great information, we get to say that WXYZ is a parallelogram. And we get to state that it's a parallelogram by the opposite sides parallel and congruent theorem. There you go. Okay, last problem is going to be a problem that I'd love for you to try out on your own. So this example down here at the bottom is going to be our you try it problem on the back. So if you could please give this one a shot, I would appreciate that. Pause the video now, and then I'll display the answer in a couple seconds. Here is your answer. So I've labeled my drawing right here with my point L in the middle. I've also put a couple of side lengths of 18 and 7. Some of the longer sides that we had, like GJ, are a little bit hard to label. This right here is where your 14 is. And this right here is where your 36 is. There you go. Now, I've done a little bit of subtraction. 14, take away the 7 that I have right down here, is going to allow me to find out that my other length is 7. And 36, take away the 18, is going to allow me to find out that my other length is 18. These are going to make a couple of matching sets of 18s and a couple of matching sets of 7s, which means that my two diagonals are bisecting each other, and the parallelogram diagonals converse is going to be the best option for me. Okay, so now it is time for you to try out some of those problems in the worksheet, and then you can check your work based off of the key that is posted as well. Good luck, and please contact your math teacher or myself if you have any questions at all on this material.